right, so today we're going to take a look at the difference between metals, nonmetals, and semi-metals. There are really four properties that we want to be focused on here. Okay, in order to be a metal, all metals have the following four characteristics. They have to be shiny, we say lustrous. They have to be malleable, which means that they can be hammered into a thin sheet. They have to be ductile, which means that they can be stretched into wires. And they have to conduct electricity. We say they're conductive. So all metals need those four things. If it's going to be a metal, it has to be shiny, malleable, ductile, and conductive of electricity. If it's going to be a nonmetal, it has none of those four characteristics. So nonmetals are not shiny, they're dull. They're not malleable or ductile. You can't hit them with a hammer and spread them into thin sheets or draw them into wires. They'll break. They're brittle. And they don't conduct electricity. They're non-conductive. And semi-metals are somewhere in between. So we're going to take a look at those four and see how that works with metals. So the first one is luster. So we said that all metals are shiny. Here are some examples of some metals. This is lead. This is some copper. Some more lead. This is a piece of tin. And we have some others here. This is some tin foil right here. This is clearly a shiny piece of metal right here. Here's a shiny piece of copper. This copper is fairly shiny. But this copper is not, and neither is the lead. And we're wondering now, if all metals are shiny, how come these aren't? This is clearly copper, this is a piece of lead. How come they're not shiny? Well, the fact is that these metals have a coating on them that happens when the metals sit out in the air for very long. It's called a patina, and it's basically the oxide of the metal. So there's some lead oxide on the cover there. There's some copper oxide here. If we want to see the shine, all we need to do is take a piece of steel wool, give it a good scrub, and you'll see that shine come right through. There's the shiny copper underneath. We can do the same thing with lead. We can give it a good scrub, and you'll see it shines up a little bit. Now these metals, copper not so quickly, but lead pretty quickly is going to revert to this dull gray because lead is a pretty reactive metal. We don't need to do that with tin. Tin actually stays pretty shiny. It doesn't react all that well with air. Here's a nonmetal. This is a piece of sulfur, and you can see it's not shiny at all. It's very dull. In order to be a nonmetal, it can't be shiny. Here's some carbon. Carbon is also not a metal. It's dull in shape. Okay? What about semi-metals? Here is some silicon. Now silicon is a semi-metal, and if you look, it's kind of shiny. So semi-metals sometimes have some of the properties of metal. Silicon has this property, luster. It is shiny. So the next property that we want to take a look at is malleability. The word malleable comes from the Latin word malleus, which means hammer. And so the easiest way to show you this is to take this hammer and whack the piece of lead. So lead is a really soft metal. So lead, the malleability is pretty easy to be seen. All I have to do is and you see it flattens out into a much thinner shape than it was. That's malleability. Now I can do the same thing to the copper or to the tin. It's just going to take more force. But all metals are soft like that to some point. Now if I want to make it a little easier, I can do what the old blacksmiths used to do, and I can heat this up. And if I heat it up, it softens it up a little bit more, and I can do that. If I try to do that with a nonmetal, say a piece of sulfur, it breaks. It doesn't actually deform like that. Okay, so nonmetals, not malleable at all. With a semi-metal like silicon, we see that it's shiny, but what about malleability? Is it malleable? Well, all we have to do is hit it with a hammer. Not malleable at all. Ductility is a little bit harder to test because it requires some machinery that we just don't have here. In order to make a metal into a wire like this is some copper wire, you heat the metal up to a fairly high temperature and you stretch it between two hydraulic arms that pull it apart into a very thin wire. Think about when you were chewing gum as a little kid and you pull the gum out into a long string. That's what ductility is. Now, if a metal is malleable, it's soft enough to be deformed that way, then it's also soft enough to be deformed and stretched into a thin wire. You try to stretch a piece of nonmetal, and it's going to snap because nonmetals are brittle, for the same reason that you can't hit them with a hammer. If we want to test to see if something is conductive, we need a special conductivity tester. Now, this is nothing more than a light bulb in a socket that's been connected to the electrical current. There's current running through there right now, but down here I have 2 electrodes, and these electrodes are not touching each other. And since they're not touching each other, there's no way for the current to get from one side to the other to light the light bulb. In order to light the light bulb, I have to complete the circuit. And the only way I can complete the circuit is either by touching those 2 together or by putting something between them that will conduct the electricity and allow it to go through. So if I take a piece of copper, for example, here's some copper metal, if I touch it to both of those electrodes, the light lights up because copper is a metal and it conducts electricity. Copper conducts electricity very well, as you can see. You might wonder why I'm not being electrocuted when I'm touching the metal and between the leads, but that's because electricity always takes the shortest path. It's much easier for it to just go across between the electrodes than to go all the way through me. I wouldn't want to put my finger in the middle, because then I'd be part of that path, perhaps. I can take a piece of lead and do the same thing. I can do the same thing with a piece of tin. Again, as long as I'm not in the path of the electrons, I'm okay. But with a piece of sulfur, nothing. Sulfur does not conduct electricity because it's a nonmetal. It has none of those 4. Silicon, however, is pretty interesting. Remember, we saw silicon was shiny, lustrous, like a metal, but not malleable, not soft and deformable, and not ductile. But silicon actually conducts electricity. Now these pieces there we go, conducts electricity fairly well. So silicon has 2 of the properties of metals. It's shiny, lustrous, and conductive. But it doesn't have 2 of the other 2 properties. It's not malleable or ductile. That's what makes it a semi-metal. It has half the properties of metal. The other semi-metals are like that. Okay? Metals conduct, non-metals don't.